Calc students, this is section 2.6. This section should be shorter than the 2.5. I apologize, my last recording was a little long, but there was a lot of new material in there. Today we're talking about limits at infinity, and that goes hand in hand with horizontal asymptotes. Okay, so first we're going to look at this graph here on number 1 and talk about limits at infinity or negative infinity, and then we'll talk more about horizontal asymptotes. I'll kind of refresh your brain a little bit about those in a minute. Flashback to algebra 2, if you will. So first of all, this graph, it says the function f, or for the function f whose graph is given, state the following. So first of all, the limit of f of x as x approaches infinity. So again, first of all, I don't like that you can hardly see the x and y axis. So this is your y axis, sorry. This is your x axis. I hate that they don't kind of bold those in. But so as x gets bigger and bigger, so you're looking over here on this side of the graph, as x gets bigger and bigger, what does f of x approach? Well, you can see here on the edge of our graph, it looks like it's kind of leveling off and it's going to approach -2. That would be my answer there. Okay. Now, the limit of f of x as x approaches negative infinity. So now, as we're going this way on our graph, okay, negative infinity, what does f of x approach? Well, you can tell if you kind of copy the line here, it looks like it's leveling off up here, and that would be +2. Now, the limit of f of x as x approaches 1, and let me also remind you that in order to get a hard limit, not a left limit or a right limit, but the overall limit, both sides of the function have to approach the same point. Okay, so the limit of f of x as x approaches 1. Here from the left looks like it's going up. Here from the right also looks like it's going up. So this actually approaches infinity, and of course that's one of the dead spots on my board. But the limit of f of x as x approaches 1 is infinity. And again, that only works because it's approaching infinity from the left and from the right side. Okay. Now, the limit, I always forget that I have to erase here. The limit of f of x as x approaches 3. So now if we're looking here at 3, okay, again, from the left and the right, we're going down here, we're going down here, okay, so they are both approaching, this would be negative infinity. Hope you guys see that, okay. Now, part E says the equations of the asymptotes. Now, let's talk asymptotes. Asymptotes are those kind of invisible lines, if you will, that the function will not cross as it gets bigger and bigger, okay, or smaller and smaller, I guess. So let's look at vertical asymptotes. Okay, vertical asymptotes. The first thing that jump out at me, those would be if we were graphing our rational functions like we did in algebra 2 or even trig. What are those kind of invisible vertical lines that the function won't cross? Well, here's one of them, okay, and it looks like here's the other. So those are those invisible vertical lines that it won't cross. So how do we find the equations of those lines? Well, if you remember, vertical lines are just x equals a constant. So this one would be x equals 3, this one would be x equals 1. Those are my vertical asymptotes. Okay, I'm not going to scroll down and write it in the box so I can keep the graph up on the screen, but those would be the vertical asymptotes. And they would want those separated by a comma in your answer box there on the first part of E. Horizontal asymptotes. Now, if you remember horizontal asymptotes, well, and vertical, technically somewhere along the line, the function can cross it, but it eventually kind of levels out at that kind of imaginary horizontal line. So those are what my limits were that I approached as I went to infinity and negative infinity. So this would be kind of my horizontal line that the function approaches as it goes to infinity, okay? And that would be what, y equals -2, okay? That would be the equation of the horizontal line. And then another horizontal asymptote would be up here, again, as the function approaches it. This is the equation y equals +2. So those are all your asymptotes. You've got 2 verticals and 2 horizontals. And again, if we extend the horizontals, does the function cross it at different points? Yes, but we're talking about where it kind of levels off. Okay, that's what we're saying. So levels off there as it goes to infinity at y equals -2, and it levels off as it goes to negative infinity at y equals +2. Those would be your 4 asymptotes, 2 vertical, 2 horizontal. Okay, visually, I hope you can see those. Okay, let's move on. So now it says sketch the graph of an example of a function that satisfies all of the given conditions. Now, a couple of things that jump out at me. I'm not going to solve this one for you, but a couple of things bother me just looking at the graph possibilities that we have to choose from. First thing that jumps out at me is this 1 right here, okay? This, what's wrong with the limit? What would I say the limit of f of x is as x approaches 1? What would the answer to that be? That would also actually be dne. Why? Because on the left side, it approaches positive infinity. On the right side, it approaches negative infinity. So the limit of the function as it approaches 1 does not exist. Okay, again, just kind of want to point out some of those things to you that you should be recognizing when you look at a graph. Now, that's one thing. And again, you can kind of look at these graphs and make your picks. But same thing could be said here on the one right below it. Again, same exact thing. The limit of f of x as x approaches 1 does not exist because from the left, it goes to negative infinity. From the right, it goes to positive infinity. Okay, so in the directions, they were pretty specific that one of the characteristics of the graph had to be that the limit of f of x as x approaches 1 equals positive infinity. So that eliminates these 2 right off the bat, these 2 on the right side. Okay, so again, a lot of times when, particularly when you have multiple choice questions, you're looking for process of elimination. I'll let you all finish that. Now, guess the value of the limit. And it says the limit of x cubed over 3 to the x power as x approaches infinity. By evaluating the function f of x equals that for all of those points. Now, you can do that, and I kind of started that. So if I plug in 0, okay, I end up with 0 over 1. If I plug in 1, I end up with 1 over 3. If I plug in 2, I end up with 8 over 9. 3, I end up with 27 over 27, which would be 1, obviously. And then 4 is 64 over 81, and so on and so forth. If you notice a pattern here, or kind of what it's headed toward, okay, I kind of stopped there. Notice the bottom number, other than the first 4 here. Here we go 0, fraction, close to 1, is 1. So here's 0, a little over 0, closer to 1, equals 1, and then we start dropping down as we go bigger. So dropping down as in the denominator is going to be getting bigger, faster, larger, quicker than the numerator. Okay, that's what we're talking about. Your denominator is going to be getting larger, quicker or faster than the numerator is. So what is that going to level out at? Ultimately, it's going to level out and tell me my limit is 0. Now, another way you can do this is, of course, our favorite tool, Desmos. So if I graph this in Desmos, again, you can kind of see I started at 0, and then when I put in a 1, what did I get? Like a 1/3, so a little over. And then when I put in a 2, I got 8/9, almost to 1. And then when I put in a 3, I actually equaled 1, right? 27 over 27. And then as I kept going, okay, my fraction got closer and closer and closer to 0. So one of the quick ways you can kind of visualize and help you understand limits is to graph the function, okay? So just kind of wanted to point that out visually. Okay, now, starting with number 4 on, I want to take a minute here and discuss horizontal asymptotes, okay? Because that's what we're going to be talking about. Now, and actually, before we do that, let me back up even further and talk about vertical asymptotes. Vertical asymptotes, because this kind of goes hand in hand with what we did the other day with continuity. If you have a rational function, now again, that is a fraction made up of polynomials, essentially, okay, a rational function. If you have a rational function, first thing you should always try to do is simplify. After you've simplified, which means factor the top and bottom, cancel any common factors. After you've simplified, any value that makes the denominator equal 0 becomes a vertical asymptote, okay? Now, horizontal asymptotes are what we're most concerned with when we're talking about limits. Horizontal asymptotes, if you remember, let me just kind of write this up here. We went over horizontal asymptotes in detail in Algebra 2. I don't know if you all can remember back, and we touched on them again in trig or pre-calc, but horizontal asymptotes, a couple of different things going on. If the denominator's degree, or let me just say, if degree of denominator is greater than the degree of the numerator, then your horizontal asymptote is literally y equals 0. Y equals 0 is your horizontal asymptote if the degree of the denominator is bigger than the degree of the numerator. Now think about what that means. If we think about that in terms of what we just did there on number 3, what that means is if you have like an x to the 4th on the bottom and an x cubed on top, whatever value you put in for x, as x approaches infinity, the bottom is going to get bigger and bigger and bigger versus the top. So that means you're going to have a smaller and smaller and smaller fraction. Okay, bigger numbers, but smaller value of fraction. Okay, so you're talking, you know, if you put in a 2, you're going to have, what did I use as an example? X cubed over x to the 4th, so you're going to have 8 over 16. You put in a 3, you're going to have 27 over 81. Again, the bottom outpaces the top. So your number, the value of your number is going to get smaller and smaller and smaller and go to 0. So that's your horizontal asymptote. Now, if the degree of the numerator is greater than the degree of the denominator, okay? So if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote, okay? So I'm going to put no horizontal asymptote. Does not exist. Okay? No horizontal asymptote. That's what my HA stands for. So if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote. And again, think back to my example. If I have now x4th over x cubed, as I put in bigger and bigger numbers of x, my numerator is going to outpace my denominator, and my number is just going to get bigger and bigger and bigger and bigger. It's never going to cap out. It's actually just going to go head into infinity. Okay, so there's no horizontal asymptote. Now, here's the last and probably the most important, the most cut and dried one. If the degree of your numerator equals the degree of your denominator, then your horizontal asymptote is the ratio of the leading coefficient of the top over the leading coefficient of the bottom. Okay, so if I had, let me just say, if I had ax cubed over bx cubed, and it really doesn't matter what's behind it. What's behind it makes no difference whatsoever. Okay, so if the degree of the numerator is equal to the degree of the denominator, okay, so I have an x cubed on top and x cubed on bottom. Again, what follows it makes no difference. My horizontal asymptote here is going to be y equals a over b. Okay, it's literally the ratio of the leading coefficient, the top one over the bottom one. Because again, the x values are going to keep pace with each other. So the only thing that's reining them in or that's controlling them is their leading coefficient multiple. So your horizontal asymptote is going to be the ratio of the leading coefficient of the top over the leading coefficient of the bottom. Okay, so that kind of brings us to this number 4 here. Now that I kind of did a little mini lecture inside your homework problems, that brings us to this problem, which this is both degree 2, right? The rest of this makes absolutely no difference. Now, if you go through the PowerPoint presentation, there's kind of a long way to do this and the short, dirty way to do this, and I'm teaching you the short, dirty way to do it. The long way is you have to divide everything by x squared, and then you have to break out the limits using the limit laws and yada, yada, yada. In my mind, when I think limits, I'm thinking horizontal asymptotes. So I'm just getting to the nitty gritty here. And since these are of the same degree, literally, my limit is 6 over 3, which is 2. That's my answer. Okay, is the number 2. I take the leading coefficient of the top over the leading coefficient of the bottom. None of the rest of the polynomial makes any difference. Okay, horizontal asymptote. I hope you guys got that down, because now I have to erase all of it to keep moving. Okay. All right, moving on. Find the limit if it exists. Now, if you remember, what did I just have in my notes a minute ago whenever we were talking about degrees of the numerator versus degrees of the denominator? On this one, the denominator degree is bigger. This is bigger than this, which would just be a 1, right? So this has horizontal asymptote. If you remember back to the notes, if the degree of the denominator is greater than the degree of the numerator, your horizontal asymptote is just y equals 0. And again, think about that visually. If I graph this, what I put in for x, the bottom number is going to get bigger and bigger and bigger faster than the top number. So that means my fraction is going to get smaller and smaller and smaller. It approaches 0. Okay, so that's my limit, is 0. Now, on this one, again, they kind of trip you up a little bit because they wrote it in not descending order here. So really, again, though, my degree is a squared and a squared. So my leading coefficients are what I'm looking at. This is a positive 1 over a negative 1, okay, which is just negative 1. So that would be the limit. Again, leading coefficient of the top over the leading coefficient of the bottom if the degrees are equal. Okay. Moving right along. Now this one's a little weird, if you will. And if you, again, if they did one of these in the PowerPoint, I didn't look all the way through, honestly. They do all kinds of strange things. I'm not going to do that. I'm, again, going to kind of show you the quick and dirty way. So I am essentially going to ignore all of this back here. And I am just looking at the square root of 9x to the 6th over x cubed. Well, if I take the square root of 9x to the 6th, that is 3x squared. Would you all agree to that? Sorry, x cubed. I apologize. X cubed. Whoa, what happened to my board? There we go. So that is 3x cubed. Okay, so 3x cubed over x cubed, again, all we are concerned with, since these are the same degree, is the leading coefficient. That's 3 over 1, or just 3. That's my limit. Okay, and again, there's a whole bunch of other steps to keep it proper, but that's the kind of quick and dirty way. Okay, now number 8's a little different animal. Because we don't have a denominator, and we kind of need one to be able to figure out what kind of overpowers the other. So first thing I'm going to do, since this is technically a binomial, again, it's ugly because that whole first term is that whole radical. I am going to write this like over the number 1, and then I am going to multiply the top by the conjugate. So 9x squared plus x plus 3x over, and again, root of 9x squared plus x plus 3x. Now, on top, remember, if you multiply conjugates, all you really have to do is multiply the first terms and the last terms. So on the top here, I'm not going to show every intermediate step, but when I multiply a radical times itself, the radical cancels. So I have 9x squared plus x, and then negative 3x times 3x is negative 9x squared, all over this gobbledygook. Okay, now, what do you notice about the top? Okay, what you notice about the top is that your 9x squareds are going to cancel, right? So now you are going to be left with x on the top over, now, this is where, again, we're looking for the first leading term, the highest power term of whatever polynomial we've got here on the bottom. So once again, I'm going to say this part doesn't really matter. If I take the square root of 9x squared, what do I come out with? I come out with 3x. Would you all agree to that? So if I take the square root of 9x squared, I get 3x. Well, 3x plus 3x is going to leave me with 6x down here. Okay, so then do these have the same degree? You betcha. Okay, these are both first degrees, right? So what am I concerned with? I'm concerned with the leading coefficient. What's the missing leading coefficient here? It's a 1. So what's my limit? 1/6. Okay, 1/6. So that would be my answer here. I hope you guys kind of see that. Okay. Now, number 9, find the limit if it exists. If an answer does not exist, enter D and E. Now, what did I talk about earlier when I said my little mini lecture on horizontal asymptotes? If the top or the numerator has a degree higher than the denominator, what does that do for me in terms of horizontal asymptotes? Okay, this is higher than this. So think about what that means as x gets bigger and bigger and bigger. As x gets bigger and bigger and bigger, the top is going to outpace the bottom, and the numbers are just going to keep getting large and large and large. Okay, so I have no horizontal asymptote. Okay, so there is no horizontal asymptote. So does a limit exist? No. This is D and E, does not exist. Okay, no horizontal asymptote if the numerator has a higher degree than the denominator. Okay, almost done. Number 10. Now, number 10, I'm going to kind of refer back to the squeeze theorem. So hang with me a little bit. We talked about the squeeze theorem, I want to say that was 2.3, which essentially means if I know there is a function that whose value is between two other functions, so it's kind of bound in the middle, and if I know the limit of the top function and the limit of the bottom function, okay, then I can tell you what the middle one is, okay? So that's kind of the squeeze theorem in a nutshell. So first of all, let me just start by saying e to the negative 4x is greater than 0. Now, if you remember your basic exponential functions, they usually all, unless they've been translated, they usually always go through the point 0, 1, and they are always above the x-axis. Now, the fact that the exponent is negative just means that it flips across the y-axis, so it's still above the x, always. Okay, so this would look roughly, bad drawing, but this would look roughly something like this, okay, if I graphed it, all right? Still, it's always going to be above the x-axis, so that function is always greater than 0. Now, let's talk about the cosine function. We also know that cosine of x goes between 1 and -1, right? Imagine your cosine curve, okay? So if you remember cosine, it kind of looks like this, right? Okay, it always oscillates between a +1 and a -1. So now, if I kind of distribute, if you will, this is maybe bad terminology, but if I take this function and multiply it essentially by all three of these, okay, then I get e to the -4x times -1 is negative e to the -4x is going to be less than or equal to e to the -4x times cosine x, which is going to be less than or equal to e to the -4x, because anything times 1 is itself. Now, what happens here on a negative e to the -4x? If this is e to the -4x is this graph that I drew over here, the negative just means it's going to flip down, but it's still going to approach 0. So what happens here is this one, the limit as x approaches infinity of this equals 0. Okay, that was some bad, like if I poke this here. Okay, so the limit of negative e to the -4x as x approaches, and then I didn't even write it, as x approaches infinity equals 0. Okay, this one over here, we already know from the graph that I drew, is the same kind of deal. The limit as x approaches infinity of this function also equals 0. So if the limit on the left equals 0 and the limit on the right equals 0, what can I say about the limit in the middle? Again, the limit as x approaches infinity of this whole function equals 0. That's the squeeze theorem, if you remember. If you remember, we had like a parabola on 2.3 on the homework assignment. We had a parabola on the top, a parabola on the bottom, one pointing up, one pointing down, and then we had some kind of sinusoidal curve in between them. Okay, but again, the squeeze theorem. If I know that a function is between two other functions, and I know the limit of the one on the left is the same as the limit of the one on the right, then the one in the middle's got to match it. So this is a big fat 0. Okay, it's a lot of work, but I wanted you to kind of understand where I was coming from. Okay, now, number 11, again, talking horizontal and vertical asymptotes. First thing that jumps out at me is this is going to be your horizontal asymptote, right? These are your vertical asymptotes, because vertical lines, the graph is x equals whatever. Now, on the horizontal asymptote, that is super easy to find. Why? Because both of these are the same degree. So how do I find my horizontal asymptote? Remember, it's the ratio of the leading coefficients, top over bottom. So this is 4/1 or just 4. So I know my horizontal asymptote is y equals 4. Now, vertical asymptotes. I can tell just by looking that these two polynomials, nothing's going to cancel if I simplify. So the top, let's see, I'm not even sure that factors of -8, that would add, no, that one doesn't even factor, the numerator doesn't. So there's nothing that will cancel. So what happens though if I factor the denominator? So the denominator factors, that ends up being x plus 6 times x minus 5. Are you guys okay with that? Now, The denominator is where I find my vertical asymptotes, if you remember. What values of x would make that rational function blow up, so to speak? Okay, what values of x are excluded? Once you find the values of x that are excluded, they either become wholes. Again, we talked about that yesterday with continuity, but they become a whole if you can cancel out that binomial factor with something on the top. They become a vertical asymptote if they don't cancel out. So these don't cancel out. So this gives me x equals -6, and this gives me x equals 5. Those would be my two vertical asymptotes. And again, they want the smaller values, so this has to be the -6. That has to be the 5. Okay, so you're solving the denominator for the values that would make it equal 0. And again, the difference between a vertical asymptote and a whole, or a, like a removable or something point of discontinuity that we talked about last time in 2.5, is that if you have a binomial factor on the bottom that will cancel with something on the top, then it just becomes a whole in the function. It doesn't become a vertical asymptote. These two binomial factors in the denominator do not cancel with anything in the numerator, so they become vertical asymptotes. Okay. All right, I'm going to stop there. That covers section 2.6 for your next part of homework. And I saved us about 15 minutes over the last video. So if you guys have any questions, don't forget about my office hours.